Hello everyone. In this video I want to tell you how to do hypothesis testing using the example of a simple two-sided t-test on the slope parameter in a simple regression model. So in the simple regression model we have one explanatory variable and the slope parameter that's attached to it is beta. We start off with a set of hypotheses. H0, also called the null hypothesis, is that beta is equal to beta 0, constant that we have to specify. H1, the alternative hypothesis, is that beta is different from beta 0. Now, how do we go about extracting evidence from the data about these hypotheses? Well, we have an estimate called beta hat of the true parameter beta. And this gives us some idea about where beta is, since the estimate should be close, in some sense, to the true value. So here's the idea. If beta hat is close to beta 0, then we suspect that beta probably also is. And maybe it's even equal to beta 0. In this case, we do not reject the hypothesis that beta is equal to beta 0. If, on the other hand, beta hat is far away from beta 0, then we suspect that beta probably also is far away from beta 0. And in this case, we do reject the hypothesis that beta is equal to beta 0. The only problem with this idea is that we haven't really defined what we mean by close. Is a difference of 5 close, or is it not so close? What about a difference of 0.1? And shouldn't it all depend on how precise our estimate of beta hat was in the first place? Indeed, it should. If our estimate beta hat is very precise, then even small differences should count as far away. Whereas if our estimate beta hat is very imprecise, even a large difference could count as close by. To formalize these ideas, let's turn the problem around. Suppose that H0, the hypothesis that beta equals beta 0, is true. Under this assumption, beta hat follows a normal distribution with mean beta 0 and variance sigma beta squared. Now, subtracting beta 0 and dividing by its standard deviation sigma beta, we obtain a standard normal distribution. At this point, I have to take a bit of a leap, so take a moment to see if you agree with me so far. The thing I want to get to is the test statistic, a number that we can calculate from the data and which will tell us once and for all how close or far we are from beta 0. And we're almost there with this one. The only issue is that sigma beta, the true variance of beta hat, is an unknown true parameter. The obvious thing to do is to replace sigma beta by its estimate, sigma hat beta, and that is exactly what we'll do. But in doing so, we change the distribution that this follows under the null hypothesis. The man who first figured this out was an employee of the Guinness Brewery. And because his employer did not want these trade secrets published, he published under a pseudonym, Student. That is why today, this distribution is known as Student's t-distribution. It depends on a degrees of freedom parameter equal to the sample size n minus the number of parameters, k. And for n minus k large, the distribution becomes indistinguishable from a standard normal distribution. Now we're ready to do the test. We've established that t, a quantity we can compute, follows a known distribution under H0. If H0 is true, t can be positive or negative, but it will usually be close to 0. It can also be far away from 0, but in that case, we can compute the probability of that happening for any given distance from 0. So here's what we'll do. We take the t that we have computed, and we see how it compares to this distribution. Then we ask again the same question from earlier. Is this far away from 0, or is it nearby? If it is far away from 0, then beta hat was far away from beta 0. If it was close by, then beta hat was close to beta 0. There's a beautiful way of measuring how close or far we are from 0, the p-value. The t-distribution describes how our statistic behaves if indeed beta is equal to beta 0. So we will compute the probability of obtaining a t-statistic that is even larger in absolute value than the one we have computed. We can get this p-value by integrating over all the t-values that are greater than the t-statistic we computed in absolute value. Because the distribution is symmetric, it is enough to do this for the positive side and multiply by 2. Instead of computing the integral from the absolute value of t to infinity of the probability density function, or PDF, we can also just read out the value from the cumulative density function, or CDF, which is the antiderivative of the PDF. The area under the curve on the positive side of the PDF is equal to 1 minus the value of the CDF of the absolute value of t. Let's call the CDF f. Then p is equal to 2 times 1 minus f of the absolute value of t. So let me recap what we just saw. The p-value is the probability under the null of obtaining a t-statistic that is more extreme, or larger in absolute value, than the one we have computed. If this probability is large, then it's time for a good shrug. The result is entirely unremarkable under h0. It is perfectly compatible with the belief that beta is equal to beta 0. It doesn't mean that we know that h0 is exactly true, of course. It just means that we have no reason to reject it. But if the probability is small, this tells us that the result we obtained is rather unusual under the hypothesis h0. It gives us reason to doubt that h0 is in fact true. If the p-value is very small, we will say that we reject h0 in favor of the alternative, h1. If you think that saying small p-value sounds like a matter of opinion, you're quite right. You can imagine people with a stake in the outcome of a test arguing over this. In an attempt to improve this situation, and also to give guidance on when to say that we reject h0, the confidence level was invented. This number, usually denoted alpha, is set by convention at either 1% or 5%, although sometimes other values are chosen. The way you use alpha is as follows. If the p-value is larger than alpha, then we say that we do not reject h0. We also do not accept h1, the alternative. If, on the other hand, the p-value was smaller than alpha, then we say that we have sufficient evidence and we do reject h0. Rejecting h0 amounts to accepting the alternative. I hope you enjoyed this video, and I hope you learned something. And remember, it will be on the test.